Alright, in this very quick video, we're only going to be looking at the structure of oxygen versus an oxygen-free radical, because in the HSC chemistry course, the students examine, I guess, the way in which oxygen-free radicals react with gases in the atmosphere to form ozone. And it's also part of the reactions when we look at CFCs and the destruction of ozone. And so we need to understand the difference between an oxygen atom or oxygen molecule and, of course, a free radical oxygen. So let's draw the Lewis dot structure of oxygen. Okay, so oxygen's got 6 valence electrons. So each atom here's got 2, 4, 6, 2, 4, 6. But then we have the formation of a double bond here. And so that is the oxygen molecule. All right, the two lone pair of electrons are on opposite sides. In fact, if I was to draw it 100% accurately, it would actually be something like this over here. All right, you'd have your double bond like that, and then you'd have the lone pair of electrons at a slight angle. Okay, because if you remember from valence shell electron pair repulsion theory, electron dense regions wants to be further apart from each other, and so therefore we form a trigonal planar geometric arrangement of the electron regions. But I've just drawn it like that, but just keep that in mind. So here we have an oxygen molecule, and if we were to look at the properties of that, we could say the number of oxygen atoms in terms of its structure. Then we could talk about paired electrons, and then we could add unpaired electrons. And so in this particular one here, the number of atoms is 2 oxygen atoms. Each oxygen atom has 2 pairs of paired electrons, and there's 0. There's no single oxygens, and therefore we can say it's very stable. What about an oxygen free radical? Well, oxygen free radical is an oxygen atom. It's still got 6 valence electrons. However, 2 of them are unpaired. So we have 2 paired electrons and 2 unpaired. And of course, being unpaired, it's a lot more unstable and therefore a lot more reactive. Oh, look at this running here. Look at that. Don't you just love how it does that? Nope. All right, so in terms of number of atoms, we've got one number of atom. Paired electrons, we've got 2. And unpaired electrons, 2. So because of the unpaired electrons, we can say it's unstable, and therefore very reactive. Okay, even this one's running. Look at that, talking about unstable. All right, so how do we form these radicals, right? Well, what happens, and we're going to find more about this when we look at the chemistry of ozone formation and destruction. If we do our Lewis dot structure here, now that I just rubbed it out and drew it again, but anyway, we get a bit of energy, right? UV radiation, right? UV radiation that's coming from the sun comes along and hits that bond, and it splits it homolytically. Lytic means to break, or lysis. Okay, for you bio heads out there, you get the lysis of cells. So lysis means to break, and homo means the same prefix. It's a homo. This is meaning the same, like homologous chromosomes. So if we think about the electrons being split equally here, then what's going to happen is that we have the 2 that are paired, but then the electrons here go back and get split evenly, but they do so as singlets, right? Not a singlet that you wear, okay, in Australia. It's a singlet. In other words, it's a single atom in its orbital, okay? And so therefore we have 2 unpaired electrons, and therefore we have 2 radicals. So when we draw that, we just go like that. We don't worry about putting the other valence pair of electrons. So we designate free radical oxygens by just writing an oxygen with a dot next to it, and so you know that's a radical. And so of course O2 plus an oxygen radical makes O3. Okay, so that's the difference between an oxygen molecule and an oxygen-free radical. Hope that makes sense. You got it all down, and I'll see you in the videos where we start to see how this relates to the formation of ozone, like that, and the destruction of ozone in terms of chlorofluorocarbons. Alright, keep doing your chemistry, testing yourself, and I'll see you next time.